Today we are talking about transformations and specifically talking about reflections and translations. So when we're talking about transformations, transformations occur on a coordinate plane. It's when we take a figure and we either move it, flip it, rotate it, or dilate it. We talk about these things in Math 6, 7, and 8, and we continue them into geometry as we move to the coordinate plane as well. Just a few things change. So first of all, overall, a transformation is just taking a figure, and it's just an operation that moves or changes that geometric figure in some way to make a new figure. Most of ours are what we call isometric, which means they don't change size or shape. The only one that changes size would be your dilation, but everybody else is isometric, your rotation, your reflection, and your translation, because they're going to take the figure and you're going to do something with it on this coordinate plane. With this, we have something called a pre-image. The pre-image is our original figure. It's the one we start with. When we have this figure, it's labeled A, B, C, or D, E, F, or by any 3, 4, 5, depending on what your figure is. The point is it's a capital letter at your vertices. Because then we talk about an image. An image is our new figure, which is produced by the transformation. When we do this, you're going to use a prime notation to show the new figure. That means, let's just say we moved him across the plane. The prime notation is this little prime right there. That's the prime notation. This indicates he is the moved figure or our new figure or our new image. Specifically, we're going to start talking about a reflection first. A reflection just uses this line of reflection or line of symmetry, same deal, to create our mirror image. We used this reflection a lot when we did quadratics. We had to take that parabola and get the other side of it. We did a reflection a lot across a line of symmetry. Same deal. This right here is my line of reflection or my line of symmetry. Same deal. This has been reflected across our y-axis, or it's a vertical, because it's a vertical line, a vertical reflection. With that, we can do several other reflections. One, we can reflect off one of the axes, which is what you've done in the past. But now that we've already had Algebra 1, you're going to see that we're also going to reflect upon like x equals 1 or x equals 2 or y equals 3, the lines that are created. We're also going to reflect across a diagonal line, y equals x in our thing. So down here, when we talk about reflections and rules for reflections, when you're reflecting across the x-axis, that's not going to be all the time. It's almost easier to count to the line of symmetry, but if you have an AB and you're reflecting across this x-axis, that's again that vertical, that horizontal reflection, so the only guy that changes is going to be your B. He's going to be the opposite. So if this is 1, 2, this would be 1, negative 2. That's what it means by the negative B. If it's off the y-axis, which again is rare for what we're going to do, then it's a vertical shift, so only our A changes. So he becomes negative A and the same B. So again, if you had 1, 2, then it would be negative 1, 2. Only thing that changes is the A, because it's the only thing that's changing is that vertical, which is the A. This is the one that gets weird, and the other one, y equals negative x, which should be on here as well. When I have AB and it's reflected across this diagonal, we're talking this diagonal, these are perfect y equals mx plus b, so y equals 1x plus 0. That's the line of y equals x. So when we're talking about this reflection off of this point, what happens is my x and y just shift. So again, if he's 1, 2, he now becomes 2, 1. That's my reflected point. When I have this negative, all it does is shift in the negative. So it still switches them, but now it's going to be negative. So like -2, -1. That's all that really changes with the y equals -x, because you're going in the opposite direction for your line that you're reflecting upon. All right, so now we're going to talk about our translation. Our translation, by definition, is just taking every point of the figure, which is their vertice, and moving it in the same direction, the same distance. With that here, remember the direction can only be up or down or left or right. It can't be a diagonal direction. If it looks diagonal, then it had an x and a y shift, which is its notation. This is what it shifted in the x direction, what it shifted in the y direction. So if depending on who your original and your moved figure is, so then I would say here, he went over in my x direction this much, because that's your x direction, my y direction this much. Remember, your x is your left and y movement, your y is your up and down movement. All right, so let's just look at some examples. I'm just going to do some examples here. So you're going to name the type of transformation described in the plane. So right here, it's just a what? Right, it's just a translation, and if you wanted to be specific, it's just a straight path. So in this case, because he's going up and down, it would just be a y movement. So my x would be the same, my y would be the only thing that would shift. Didn't ask that, we're just adding it on. So here, that's obviously a reflection over the y-axis, which is considered a vertical line. Right, because it's our vertical line, so it's called a vertical reflection. If it comes up. It doesn't come up very often, but every now and then they throw that in there, so I just want you to be aware of it. All right, so now we're actually going to do some work. So now we're going to take this figure with these vertices, and we're going to sketch it after its translation. We're going to sketch the original and its image after it moves. So this is a transformation notation, which we saw up here at the top. So with this right here, when I'm talking, here's my A prime. Oh, sorry, it's my A. Sorry, my regular A, not my A prime. Let's back that boat up. That's just my regular A. Sorry, taking that right off. I have my B. I like to write things out. I have my C, and I have my D. So with this right here, it's telling me that I'm taking away 4. I'm going down 4, or sorry, excuse me, left 4, because I'm going the negative direction 4, and I'm going up 2. So I can either count it onto my coordinate grid, or I can mathematically do it here. Because mathematically, what's changing is I'm taking that x, I'm subtracting 4, he should end at -3. I'm taking that y and I'm adding 2, my new point should be -3, 4. So you're substituting in that x and that y to get that new ordered pair for my translation. So here I should have -1, 5. I should have what? 0 means he's still going to be on the, he's going to be now on the axis. -1 plus 2 is +1. Here I'll have -3 and 0. He's on the y-axis. So now let's actually plot them and count them and see if we get our same things. So we can take a few shortcuts if I don't have to plot my solution. Depends. So let's go ahead and do this first one. I got 1, 2. He's my A. I label everything so I know what I'm moving. I have 3, 3, 4, -1, and 1, -2. So here is my original figure, which just is a quadrilateral, nothing fancy. So now I want to move him. So when I go to move him now, I'm not gonna look at this. I'm just gonna say, okay, I want to go over 4 in the left, and I'm gonna go up 2. So each point, 1, 2, 3, 4, up 2. That's my A prime. 1, 2, 3, 4, up 2. That's my B prime. Sorry. 1, 2, 3, 4, up 2. That's my C prime. 1, 2, 3, 4, up 2. That's my D prime. So notice how I moved everybody the same distance. Notice in the regular notation it says plus. That's why he's in the negative direction. and he's up because that's the positive direction. It all goes with my coordinate grid. So if I have a positive, that's negative direction, and positive direction, just like when you're moving stuff regularly. So let's just see if I got it right. Negative 3, 0, 0, 1, 1, negative 1, 5. Yep, so my math was correct. So you can do either way. It depends on what they're asking for. If they're asking for the coordinates or they're asking for the image. All right, so now we're going to cut out a figure, and we're going to use a reflection across the x. So you can either say, all right, I can count them, so use the reflection and draw the other half of the figure. So if I'm just drawing the other half of the figure, there's really nothing to write here. So if I'm reflecting this point here, he's already on the axis, he's going to stay on the axis. Same with that point there. But this guy here is 1 up, so he's going to be 1 down from the y, because remember, it's equidistant. This is my line of reflection right here. That's my line of reflection. So I have 1, 2, 3, 4. So I'm going to have to count 1, 2, 3, and 4. He's up 1, he's up 1. So it's going to kind of look like sketchy. I'm not a good artist, but that's okay. And there is my reflected image. Didn't ask for anything else, it just asked for the reflected image. All right, it says the vertices, triangle PQR, are at PQR. So I'm going to just write them down so I can see them clearer, because you know how I am. It says I'm taking this and I'm going to add 1. I'm going to go, to the right 1, because that's right. I'm going to go down 6. Describe the translation. Show that they're congruent to verify that your translation is a congruence transformation, which means it's isometric, which the only way you could do that is the distance formula. That's the only way. So let's go ahead and move him. So I want to go ahead and do my 2, 2. My Q is 3, 4, and then 5, 2. That's my original. Now I'm going to go ahead and move him. So my P prime, my Q prime, and my R prime, because that's my new image. Yes, I need to write that down. So now I'm going to go to the right 1 and down 6. Right 1, down 1, 2, 3, 4, 5, 6. There is my Q prime, so he's at 2, negative 2. Here I went right 1. Oh, I went left instead of right. Sorry, I went the wrong way on that first one. Nobody stopped me. Okay, guys. Let's do that one again. Sorry. Nobody stopped me. I went the wrong way. I went left instead of right. Sorry. Let's do that one over again. Sorry. We went right 1 and down 1, 2, 3, 4, 5, 6. This is where the math would have been better. So he's at what? 5, negative 2. So let's just double check him since I messed him up. So plus 1 should be 4. Oh, he was at 4. I can't even count. 4 down 6 is negative 2. So he's at 4, negative 2. Wow, that point did not want to happen. All right, 4, negative 2. Then I went 1, 1, 2, 3, 4, 5, 6. Better off if I do the math, huh? So he's at 6, negative 4. Add 1, subtract 6, right? And then I'm going to add the 1, and I'm going to subtract the 6. So he should be at 3, negative 1, 2, 3, 4. And don't forget to put the primes on your new image. Now, when it says to verify that the translation is a congruence transformation, you got to do the distance formula. The only way you can prove that he's a congruent transformation is prove all 3 sides are congruent. So we could do that on this one quickly. But you're going to do the distance formula now 6 times. So my first side, PQ, we'll do 2 of them, because if the 2 of them match, the third has to, right? So equals the distance of, for PQ, 3 minus 2 squared plus 4 minus 2 squared. So it is the square root of 1 plus 4, the square root of 5. QR, square root of 5 minus 3 squared plus 2 minus 4 squared. So it's 2 squared and 2 squared, right? So it's 2 squared is 4, negative 2 squared is 4, so it's the square root of 8. So if 2 match, we'll assume the third is going to match as well because their distances are only so long. Well, I could just do them all. Let's not assume anything, right? PR, it takes 2 seconds to do the distance formula. 5 minus 2 squared plus 2 minus 2 squared is going to be the square root of 9 plus 0, so it's the square root of 9. All right, so now let's come back here and do P prime, Q prime. So 4 minus 3 squared plus negative 2 minus 4 squared minus negative 4, so plus 4. Square root of 1 plus 4. So he matches, so that's good. We know that he matches. QR primed is going to be 6 minus 4 squared plus negative 4 plus 2 squared. So it's going to be 6 minus 4 is 2. No, yeah, 6 minus 4 is 2 plus 2, square root of 8. So they match. And so then you really need to do the third side. I've run out of room, so we're just going to do them down here. P and R, square root of PR is going to be 6 minus 3 squared plus negative 4 plus 4 squared. So it's going to be the square root of 9 plus 0. So I got the square root of 9. So again, some of that math you can do quickly onto your Desmos is no problem. But I have verified that it's isometric. Sometimes you must do a mathematical proof. You do it a lot in Algebra 2, so or trig. You do a mathematical proof. That's a mathematical proof. I've just proved that they are the same. So it's a mathematical proof. All right. Let's move on to the next one. I want to graph a quadrilateral with these vertices and find the image of each vertex after this transformation. Then graph the image using the prime notation. So negative 2, 6 is A. 2, 4 is B. 2, 1 is C. And negative 2, positive 3 is D. So here's my quadrilateral. It looks kind of like a parallelogram, but I never make assumptions. So now I want to find the image. So now if I want to find the image, I'm going to do the easy way and do it with the here. So I have A prime. So here's my thing. So it's going to be negative 2 plus 3. So I should be at 1. 6 minus 3 is 3. B prime should be at 2 plus 3 is 5. 4 minus 3 is 1. C prime should be at 2 plus 3 is 5. 1 minus 3 is negative 2. And then D prime should be at negative 2 plus 3. 3 minus 3 is 0. So that should be where they go ahead and do their translation. So let's see. I'm at 1, 3, A prime, 5, 1, B prime. C prime is at 5, negative 2. And D prime is at 1, 1, 0. There's D prime. And it looks like it shifted pretty good. I could double check here and just make sure and count them if I wanted to verify that I counted correctly. All right, it says write the rule. Now this is where you've got to be tricky. It says write the rule going from here to here. This is, if you look, the regular. This is hard to see, but that's got the primes on it. This one here's got the primes. So this is my regular figure. So I'm going from here to here. We know that the rule starts with x, y, and my arrow. Something happens to my x, something happens to my y. That's what goes on with the rule. So now, I'm at A. From here to here is what I did. So I actually went up 2, I went over 1, 2, 3 to the left. But you got to remember that this is my x, this is my y. So now I went left 3, up 2. So let's check the other ones. Left 3, up 2, left 3, up 2. It works for there. It works for there. I'm perfect on this problem. And it says to verify the transformation's isometric. I would have to go back and do all those distance formula again. I'm choosing not to. All right, number 7. Number 7 says, hey, I have these vertices at A, B, C, D. I want to graph their reflection described in this line. So here, when I'm talking about this line, you need to remember if it's x equals 2, that is going to be my VUX. Vertical line, undefined slope, x equals equation through 2. So it's going to be a line like this. That is my reflection line. So now when I go to graph, I'm just going to put my originals on here. So I have 1, 2 is my A, 3, 0 is my B, and 5, 1, 2, 3 is my C. So now, look, this is kind of wonky. He's like in the middle of the whole darn thing. But now when I'm going to do my reflection, I just have to remember whoever side he's on, he's going to be on the other side. So here, if I'm looking at my A being 1 away from this line of reflection, he's got to be 1 away for the prime on the other side. If B is 1 away on this side, then B prime has to be 1 away on the other side. It's kind of the easiest way to do it. C is 1, 2, 3, so he's 1, 2, 3 for my C prime. So now he's basically spun around and reflected on that straight vertical line. So now I'm looking at the line here. Oh, and it says line N. So if we wanted to, we could call him the N. Sorry. All right, so now I'm going to reflect among my y equals 3. So y equals 3 is my HOI. You're not going to do some weird line. You're only going to do x equals, y equals, and then my diagonal. That's all you do with the reflections. So this is my HOI, my y equals equation. So it's my horizontal line through 3. He has a slope of 0. Line M. So I see which one. All right, so again, my original figure was 1, 2. There's my A. 3, 0. There's my B. And 5, 1, 2, 3. There's my C. So now I want to reflect him on this line y equals 3. 1 away, A prime. 1, 2, 3 away, 1, 2, 3 away, B prime. C is on the line. C prime is going to be the same spot as C. There we go. And last but not least, my last two here. Here I have a line CD. C is at negative 2, 2. There's my C. My D is at 1, 2. I want to reflect across this line y equals x. So I need to remember that my line y equals x is the same thing as y equals 1x plus 0. There is my y-intercept, my slope being 1. So we go straight through my axis and comes up 1, 1, 1, 1, down 1, 1, 1, 1. And it's a nice, pretty diagonal line through the parent graph of y equals x. That's our parent graph for our regular line. It's a perfect line, 1 slope, 0 intercept. So now I want to reflect it. This is one where I don't like to think. So it's hard to think, okay, if he's there, he's got to be there. If he's reflected, he's got to be there. It's weird. So I take my points and I use the rule. This is probably the only one I probably use the rule for. If I'm reflecting across this line, that was my A and that's my B, my reflection just changes my ordered pair. So my reflection is going to be at 2, negative 2, because they just switch, and at 2, 1. So let's see if that looks right. So I'm at 2, negative 2. Why does that look weird? 2, negative C. Oh, that's at C. I'm like, why does that look weird? And my D is at 2, 1. There we go. At 2, 1. I said, no, something looks wrong. And it does. If I squished it together, if I took the paper and folded it on this line of reflection, boop, 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 like this, they would land on top of each other. That looks like a weird reflection because remember, it's like a line of reflection. So when he's diagonal, it's going to make a weird diagonal. So if I took like my paper and I went like, ooh, does it match? I'd have to like do a line and see if it matched. That's what you're doing. That line of symmetry, that line of reflection, they are the same thing. So now when I look here, I'm just going to come back over here and put my CD again. He's at what? Negative 2, 2 is my C. My D is at 1, 2, wait, 1, 1, 2, sorry, there's my D. So now I want to reflect him across the line y equals negative x. So that's y equals negative 1x plus 0 because he's going the other direction. Perfect line through my origin, except for I'm going to go this way with everything. I'm going to do my slope really quick so I have some points to hit. So again, because I don't like to have to think, I know that C is negative 2, 2. I know that D is 1, 2. So now I know that that's my A and that's my B. When it's the negative, it just switches still like before, but now they both become negative. So when I have that negative, they both become negative, or opposite. So he becomes negative 2, positive 2, because he became negative, he became positive, he became negative, he became negative. So when it goes that opposite direction, you got to do that negativity. So I have negative 2, negative 1. That's going to be my D prime, sorry. And then my C prime is negative 2, 2. So my C prime is actually on the same point again. And now he looks like that. Now he looks like that. So what you're going to work on right now is the next page in your notes packet. You have here, it's a front and back on translations and on reflections. So it's a page 6, front and back. Have a great day. If you have any questions, just ask.